Hello, everybody. This is Alex Cole here from BobCAD-CAM. What I wanted to talk with you today about was a 5-axis toolpath and controlling the tool using tilting strategies. It's come to my attention that a lot of people are struggling with understanding how the tilting strategies work and how you can control the angle of that tool when cutting different parts. When working with a multi-axis toolpath, you can control the angle that the tool is tilted on the tool axis control page found in the operation parameters. Now, on this tool axis control page, there are many different strategies we can use to control the angle that the tool will be tilted on during that cutting operation. Those strategies are defined in the drop-down next to the tool axis will label. So these different strategies vary in the tactics or the way that they're applied. We can be tilted relative to the cutting direction, so that's the direction that the tool is moving across the workpiece. We can be tilted with a fixed angle. We can be tilted with a fixed angle relative to an axis. We can also be rotated around an axis, tilted through a point. Now, this is one that is very useful for certain job types. And what it allows you to do is define a point that tool is tilted through. The same applies for the next option, which is tilted through curve. So tilted through curve is also very nice when you're wanting to control the angle of the tool relative to some feature on a part where that will actually be changing, and we can define a curve that tool will be tilted through. We also have tilted through lines, tilted from point away, and tilted from curve away. To get started, we're going to look at be tilted relative to cutting direction. Now, all of these strategies use a little bit different inputs and parameters to define how they work. The be tilted relative to cutting direction gives us the ability to define a lead lag and a side tilt angle that's relative to the direction that the tool is moving. So this is handy for a wide range of parts that you might be working on, and we're going to start looking at these options. I've started by just creating a simple job using a 5-axis machine. I've got a 2-inch by 2-inch square surface, and let's go ahead and start setting up our feature. So I'm going to create a mill multi-axis feature. I'm going to do morph between two curves. Going to the tool page, I'm going to turn this into a ball end mill by giving it a corner radius that is half the tool diameter. For my first edge, I'm simply going to select this left edge. For the second curve or edge, I'm going to select that right edge. And my drive surface is going to be the surface itself. Now, to keep the tool path not looking too cluttered, I'm going to increase this step over just so that we don't have nearly so many passes on it. Now, the tool axis control page is what we're going to be looking at mostly here. And I'm just going to leave everything at the default and go ahead and compute this tool path so that we can see what it looks like. And you can see we have just straight cuts going across our surface. The tool itself is straight up and down. And we'll backplot this just to get a quick view of how it's cutting. Now, it's okay right now that it's cutting one way. You know, for what we're looking at, this is just fine. So let's go back into the feature or the operation itself and look at the parameters on that tool axis control page. So on this page, we can control the tilting of the tool, the way that the tool is going to be angled. We're going to get into this top section a little bit later. We have options for the output format and the tool axis will, so that's our tilting strategy. Right now, the default strategy is be tilted relative to cutting direction. So this is the direction that the tool is going. And what I'm going to do is come down, and the first option we're going to look at is lead angle to cutting direction. And what does this do? So this is going to tilt the tool forward as it's cutting along. Sometimes this is necessary for orienting the tool so that it can clear apart. Sometimes it's desired so that the tool itself is not cutting right at the center of the ball tool for the contact point. Get it up on that radius a little bit so that you can get more chip clearance where the contact is on the tool. So what I'm going to do is I'm going to set this angle at 25 degrees, and I'm going to compute that tool path. Now if we look at this tool path, we can now see that everything is slanted by 25 degrees in a forward motion. So what that looks like when we backplot this now, we can see that our tool is straight up and down going from front to back. But looking at it from a side view, right, we can see that our tool is clearly tilted by our 25 degrees. All right, so, and that entire path there, each pass is tilted that even 25 degrees, and it's tilted forward. Now, if I wanted to tilt that tool backwards, I could simply go in and set this value to a minus 25 degrees, and it will tilt the tool backwards. So now the point of the tool is actually leading, and the tool is somewhat plunging, if you want to think about it that way, as it goes across that surface. Again, sometimes it's necessary to be able to kick that tool so that you can get into a specific area on a part without the shank of the tool or the tool holder colliding into something else. Now let's take a look at the side tilt options. This is very similar to the lead lag in that we can control, like we did tilting forward and backwards with the lead lag angle. We'll set that to 0. The side tilt, we can tilt that tool to the left and to the right as it cuts. So let's set the side tilt option to 25 degrees, and we'll compute this tool path. And now looking at the cut, we can see that our tool is now tilted to the side relative to that cutting direction. And once again, as we spoke before, this is applied to all of the passes in this operation. So if we set that option to a negative value, we can tilt that tool to the other side. So if I do minus 25 degrees and I compute, our tool is now tilted to the right. And that is the side tilt. Again, this is very useful for when you're cutting up next to a wall and you need to tilt a tool or keep a tool away from that wall or overhang. So some of the other options that are available for these tilting strategies when we are tilted relative to our cutting direction. There's advanced options here that allow us to alter or manipulate the effect of lead lag and side tilt as we're cutting. So let's take a look at what options we have available in here. We have a gradual lead angle change and a gradual side tilt angle change option. So what these options are actually going to do is over the course of the tool path that's been created, it will alter or apply a change in that shift. So to illustrate this the easiest, what I'm actually going to do is go back here and I'm going to set our side tilt angle to 0. And then in the advanced dialog, I'll set the gradual side tilt angle change to a value of 25 degrees. And let's take a look at what that does with our toolpath. When I compute this, we can see that our toolpath over here at the left where we're starting is straight up and down. But as that toolpath continues across the surface, it begins tilting that tool more and more till eventually this last pass has a full 25 degrees of side tilt angle applied. So again, if I backplot this, we can see that our tool is straight up and down. But as this continues across the path, okay, I'm going to go to a front view, we can see that our tool is tilting more and more. So this is very useful when you don't necessarily want to tilt the tool the entire time, but you do need to tilt that tool more and more as the path continues so that you can try to avoid colliding with either the part or fixturing. The next tilting strategy that I want to look at is using a point to define a spot where the tool is going to go through that point and point that tool relative to that point as it's cutting on the surface. So to do this, I'm going to the Create 2D menu, and I'm going to create a point. In this particular case, I'm going to create an arbitrary point up in space. So we'll set this point maybe 5 inches up in Z, and we're just going to leave it at 0, 0 to start with. So there's our point on the screen. We can see that that's a point that is centered on that surface. And you're going to be able to very quickly see the effects of using this point in the toolpath for tilting the tool. So I'll edit my operation. I'll go to the parameters and the tool axis control page. And under the tool axis wheel option, I will select this tilted through a point. Now, when we tilt through the point itself is going to control the angle that the tool is on, but we can still alter that using some of the extended options with tilt angle and so on below. I'm going to choose tilt point, and I'm going to pick the point that I created in the CAD workspace, and we can see that it has X, Y, Z, and the Z is 5 inches. Now we're also going to manipulate those values here in a little bit so you can see moving that point around and what it does to the toolpath. Everything else at this time I'm going to leave at the default setting, and I'm going to compute this toolpath. And if I zoom in here and we take a look at what that has done to this toolpath, we can see that these lines are both tilted in if I go to a right side view. And if I zoom to where our point is in the screen, you can see that these lines are all pointed right at that point that we have defined. So the tool angle is pointed there as well. So if I backplot this from the side view, you can see that as the tool cuts across, the tool is always going through that point on the surface. Okay, now this is a side view currently, but let's rotate this around and look at the front view. And also from the front view, we can see that this tool is always running through that point that we have defined. So this is very useful when trying to control something like a porch style tool path or cutting a pocket where you want that tool to be tilted away from the walls as you're cutting with the spherical contact point on that tool. So if we go back to a top view, that point is currently right in the center. And looking at this back plot, we can see how that tool is always pointed basically at the center of this rectangle at that point that's 5 inches up in Z. So let's go change where that point is, and I can either physically move the point or create a new point, or I can just come in and modify the values inside this field. We're going to set our X -2 and Y -2 so that we get the lower left-hand corner. And let's compute that tool path and see what happens. Okay, so looking from the right side view, we can see that this front edge is straight up and down and the back edge is angled. If we look at a front view, we can see that this is pretty much straight up and down, though that pass is not right exactly on the edge of our surface, and this edge is angled. So looking at the top and back plot this, we can see our tool is starting straight up and down, and then as it cuts, it's always running through this point. And as it works its way across, it's also tilting to the side. Now this is an extreme example. I probably wouldn't use something like that as much in real life. However, it illustrates exactly how that point can be used to control the angle of that tool as it's cutting an operation. Okay, next in this video, what I'd like to cover or like to show is a little bit more of an applied example or an example that's going to illustrate some of the differences between the tilted relative to cutting direction and tilted through a point. So on the screen now I have a rectangular surface where from the top view I simply took a spline and cut that edge so we can see that the same tool path, we've got one straight edge, we've got this curved edge, and what that's actually going to do to our tool path. So creating the same multi-axis morph between two curves, surface-based 5-axis tool path gives us a tool path where the tool is going straight across the part, and then as it gets over to that other edge, it starts blending into that profile so that that last pass is following the profile of that edge. Now, what is that going to do with our tool tilting strategy? Let's take a look and see what happens. So I'm going to edit my operation and go back to the parameters page and the tool axis control page. Now on this page I'm set to be tilted relative to cutting direction, and I'm going to apply a side tilt angle of 25 degrees and compute that tool path. Now looking at the front view, we can see that 25-degree angle is applied. And then looking at the right side view, we can see that the beginning of our tool path is vertical, but towards the end, we can definitely tell that it's not necessarily straight up and down. And you're going to understand why here in just a moment. So when we look at that front view, what we don't see is the path or the lines that represent what the tool angle looks like in the middle of these passes. So let's backplot this and actually take a look at what happens. Now, on this left side of the part, the tool is staying tilted at that 25 degree angle like we had it set up for. And if I actually backplot all the way through, you can see as it gets closer to the right, there's definitely some wiggle happening with the tool. And that is because of those curves. So let me back up the back plot, and this time we'll go to a right view. And as I back through this pass, you can see our tool is most definitely also changing kind of a lead and lag angle. And what that is because of, if I go all the way over to the last pass, it'll be the easiest to see it. So along this last pass, we're going to have that full angle is applied. But remember, this option is called relative to cutting direction. So because this curve is not straight, the direction that the tool is cutting is changing. And when that changes, the system is applying that 25-degree side tilt angle to the perpendicular point of where the tool is on the path, thus resulting in that tool not just being kicked to one side, but being kicked to the side based on the direction that the tool is cutting. So this results in rotations not just in a single axis. So again, the option that we're looking at is this tilted relative to cutting direction. And that just simply means that whatever the direction is that the tool is moving is the direction that that tilt is applied. Okay, so now what I would like to show you is using the same part with the curved edge. I would like to show you the effect of using a point similar to what we looked at earlier with the rectangle surface without the curved edge. So to do this, first I'm going to create my point. Now I want this point to be about the 9 o'clock position. Looking at our part from the top view, we're going to go 5 inches up in Z as we did before. So our X value is going to be -2, Y will be 0, and Z will be 5 inches up. So when I say OK, that creates my point in space. If I look at that from the top view, I can see it's right there at the 9 o'clock position. So rotating this around, what I'm going to do is enter the feature and edit that operation. And on the tool axis control page, I'm going to change that option to tilted through a point. And then on the tilt point, I'm going to select that point that we created. Okay, and looking through all the other options, I'm going to go ahead and compute this tool path. And from the front view, what we can see is this front or this left edge is pointed through our point, and the right edge here, we can see that all of those lines are tilted through that point. So when I backplot this, I can see that that tool is always pointed to that point. Looking at the right side, we can see that tool is always pointed through that point. So even once we get over to the side where the edge is curved, we will see that that tool is cutting that curve, but even at that position, the tool is always going through that point. So there's a better applied example similar to like port machining that I will be showing next, but I just wanted to show you real quick on a flat surface what that looks like. Now let's look at an applied example of using tilt through a point on more of a port style or a cavity type feature that we need to cut, and we want to control that tool. So what I've created to illustrate this point is I simply took a rectangle, I cut a cavity down into this rectangle that has a 5-degree draft on the walls. There's a lower radius and a top radius up at the top. So, all right. To create the feature, what we'll do is create our multi-axis feature. We're going to do morph between two curves. On our tool page, I'm going to use a 1/2 inch diameter end mill and set the nose radius to 250, which will make a ball end mill. And for my first curve, I will pick the top edge. For the second curve, I will pick this bottom edge. And the surfaces that I will pick will be the top radius, the wall, and the bottom radius. Now, when creating a multi-axis operation like this, I always recommend that you start by getting the path on the surface first that you want. Once you have the path on the surface, then go in and start worrying about your tilting strategy to eliminate gouges and things of that nature. So I'm going to go ahead and compute this tool path and see what the result is. Now looking at this tool path on the surface, ignoring all of my linking moves right now, again, right now I'm focused on the path on the surface itself. Right now these look very uniform and clean, and I'm happy with that result. So now let's go in and we'll take the next step, which is cleaning up the tool axis angles, and then finally we'll get our retract moves the way that they need to be. So let's go back into the feature, and we're going to look at the tool axis control. Now here we want to tilt through a point. So when we put this on the tilt through a point option, we first need to have our point that we're going to select. I could simply type numbers into this box, but to make it easier for you guys to see what I'm talking about, I'm going to actually come out and create a point first that is right above my cavity. So we'll do create point, and I'm going to create a couple different points. I'm going to create one that's at 4 inches, and I'm going to create one that's at 15 inches. Okay, so we have 2 points up above that, and we can see that they're right in the center. And I want to show you what the difference between the two are. So first we're going to use the 4-inch point. So we'll edit our operation again, and we'll go back to the tool axis control page. And on that tilt point, I'm going to pick the point that is at 4 inches. And when I compute that tool path, we can see that the path now has changed, and my lines, my retract lines, are showing that they're going in the direction of that point. If I back plot this, and I'm going to go to a front view so it's easy to see. Okay, now the tool is starting down, and it's actually violating my part. That's because we haven't defined the retracts yet, but we're going to get to those. But here we can see as I step, I can see that my tool is positioned to where it's actually going right through that point, and it's coming down to the part, and it starts walking around. And we can see that that tool is staying located through that point, and it will continue to do that as it works its way down into that cavity. That tool is always going through that point. Now, the one thing I want you to notice here, let me get the tool in a position, is that we're actually cutting with the spherical contact point of the tool for this operation, and that's what I want it to be doing. If I wanted to actually cut this angle with the side of the tool, I would be using a different toolpath strategy to do that. The tilting strategy that we're using right now is not intended for you to be machining with the side of the tool. It's how we can control when we're actually surfacing using the spherical portion of a tool. So as we go through, this is actually an acceptable tool path for what I want, except for our links and retracts. And just so we can go ahead and clean this up so that it looks better, let's go ahead and edit that operation, and we'll go fix those real quick. So going to the links tab, I'm going to go to my retracts page, and by default the system goes to a plane in the z-axis, and it's right now set at 1 inch. Well, 1 inch isn't high enough above my 0 to clear the part, and that's why we're actually going down into the part. So I'm going to set this at 2.5 inches, which will give us plenty of clearance to actually come up and out of that hole. And now you can see that we're actually a 1/2 inch above that top surface on the part, and all of that gouging motion that we had is now gone. Okay, so we've seen how backplotting and using this method, this tool, even though there's an undercut in this part, this tool is walking around on the surface. It's not violating that undercut, and it's actually machining exactly where I want it to on the wall of that undercut region. And it's going to do that all the way down to the bottom. Let's get this to where we can actually see it there. And there we're getting right on that radius. Okay, looks like we've got a couple more passes down at the bottom where it cleans that up. And boom, right there, nice clean radius on the bottom. Okay, so what happens if that point isn't located properly? Again, the point is defining a line directly through the center of the tool down to where the system is calculated that contact point is on the the tip of the tool. So if we were to do that same thing, only our point was not in the best location, the effect that it can have on the tool path could result in a gouge. So if I come out here now and I pick my point that's up at 15 inches and I calculate that tool path, we'll see that this tool angle is much shallower. And if I backplot this, we can see the result of that as we get down in here, right, is going to be that we actually violate the draft angle, the undercut angle on that wall. And that would leave us with gouging our part, and we don't want that. So, knowing where to put that point is something that is going to be application specific. Understanding that the further the point away is from the surfaces you're machining will make those angles shallower, and sometimes that's desirable. Sometimes you need it to be very steep. For those of you that are on table machines and things like that, you have to be aware of what the travel limits are on your table and on your machine. And sometimes manipulating that point and getting it in the right place is going to determine whether you have an over travel because of the tool path that you're creating. Once you go to post-process it, you'll get an over travel. Or if you have the point positioned right, it could keep you from having an over travel, yet you can still reach all of the regions of the part. So again, this is something that I use common for porting. There's some other methods that we can use as well, using curves and things like that, and we'll get into those in another video. But hopefully this shows you a little bit of how tilted relative to cutting direction and tilted through a point can be used, and what they actually do, and gives you a better idea so that when you're trying to apply those strategies to your parts, you'll be able to have more success.